The material that I'll be presenting today is the result of collaborations with Dr. Todd Hedrick and Jun Koo. Now, the basic goal of the multivariate percentile power method transformation is to take distributions that look like this and transform them into distributions that look like this, or like this, or like this. Just depends on the exact non-normal distribution that you want to produce. Now, we'll use a polynomial transformation to do this. We'll call it P of z. Here, z is a standard normal random variable, and it has probability density function as shown here, and cumulative distribution function as shown here. Now, the c sub i's are the polynomial coefficients, and we're going to need to solve for those using a moment matching technique, and I'll talk about those later on in the talk. I'm going to actually discuss two of them. One is just a conventional moment matching technique, and the other is a percentile technique. So for starters, let's look at what happens if we go ahead and set m equal to 4. This is the conventional, what we call a Fleischmann third order power method transformation. And this was originally developed in Alan Fleischmann's 1978 Psychometric article. It's a seminal work in this field. And what we have is a system of equations that's based on the first 4 moments. So we've got the mean, the variance, the skew, and the kurtosis. We'll specify values for those first 4 conventional moments, and then we'll go ahead and solve the system of equations for the polynomial coefficients. Now, alpha 1, the mean, and alpha 2, the variance, those are typically standardized, so their values are fixed to 0 and 1 respectively. And so that just leaves us focusing on distributions that have particular levels of skew and kurtosis. But the question I'm asking today is, what if we don't have those measures of skew and kurtosis? What if we're working with publicly available reports and we don't have access to individually identifiable data, individual records from which we could calculate the skew and the kurtosis? What if the person who posted the report did not provide, didn't think to compute skew and kurtosis for us? Now what can we do? Well, it would be convenient if we had a method that could work with common publicly available statistics, things like percentiles. It would also be great if this method performed at least as good as this Fleischmann third order approach. And then it would be especially convenient if it provided unique closed form solutions for those coefficients. I can tell you there are some other methods out there, but they use numerical methods to solve for the coefficients. And there's some problems with using numerical methods. For one thing, it's computationally intensive. Another problem that we find with these methods is that in one of them in particular, there are up to 4 different solutions for the polynomial coefficients. And then we can go the other end of the spectrum. For one of the other approaches, it's not guaranteed to converge to a valid solution. And so we end up with all these problems. We can avoid those problems if we just have a closed form solution. So in order to accomplish this, we're going to need to introduce 4 moment-like parameters that are based on the percentiles. And these have already been introduced by Karayan and Dudovitz in 2011. And they are the median, the interdecile range, the left-right tail weight ratio. That gets to be a little bit of a mouthful, so you're going to hear me throughout this talk, and this is not standard convention at all, but you'll hear me refer to that sometimes as percentile skew, because it reminds people that that's the parameter based on the percentiles that is similar to our measure of skew. And then the tail weight factor, same thing. I colloquially refer to that as percentile kurtosis. Now, just like with conventional moments, there are some restrictions on the values that these parameters can take. So, for example, just like the variance, the interdecile range has to be greater than or equal to 0. Actually, the same is true for the percentile skew. it also has to be greater than or equal to 0, which may leave you wondering, okay, well, what value of percentile skew does a symmetric distribution have? But you notice here that it's a ratio. So when we have a perfectly symmetric distribution, the ratio is equal to 1. So we have a symmetric distribution with a percentile skew equal to 1. And then finally, the tail weight factor, that value has to be between 0 and 1. So it's very much like a percentage, a probability or a proportion. So how do we go ahead and achieve a polynomial transformation based on these 4 parameters? We're going to do it in 3 pretty basic steps here. We will take the percentiles of the standard normal distribution, and so those become our z's. Substitute those into the polynomial expression, which is the very first equation that I put up on the slides. And then take those polynomial expressions and substitute those in to the 4 moment-like parameters that I just had on the previous slide, which are the gammas. And so that's exactly what we've done here. If we solve this system of equations for the polynomial coefficients, then what we have is this closed form solution here. And we just have one caveat to this closed form solution, which is that not all values of the percentile skew and the percentile kurtosis, not all combinations, are going to produce a valid PDF using this method. So this figure depicts the region in which we have valid solutions. So percentile skew is on the x-axis here, percentile kurtosis is on the y-axis, and any combination of values inside this region will produce a valid PDF using this transformation. Because we have symmetric distributions at percentile skew equal to 1, I went ahead and put a reference line in. That represents our symmetric distributions that we can produce with this method. So getting back to our closed form solution, I just want to summarize a little bit. There's nothing new on this slide. But if this is our closed form solution for the polynomial coefficients, what we will do is we will obtain our percentiles, and we need 5 of them. We need the 10th percentile, the 25th percentile, the 50th percentile, the 75th, and finally the 90th percentile. If we go ahead and plug those in to our solution here, we'll get the polynomial coefficients. From there, we go ahead and plug those into the P of z formula, so now we've got our polynomial. That is the transformation. From there, we go ahead and we simulate a standard normal random variable. And once we have these 2 things, we can go ahead and transform our values of the standard normal random variable using the polynomial transformation. And that's how we end up with the non-normal distribution. This is the univariate percentile power method transformation. So what do you think we need to do if we want more than one non-normally distributed variable and we want those variables to be correlated at some specified level? Well, for starters, we're going to have to start with correlated data. If we want to end the transformation with correlated data, we're going to have to start the transformation with correlated data. And so this is just a simple example here. Let's think about 2 variables. The first variable, our standard normal random variable that we simulate, is z sub j. And we go through the process that I just showed you, and we produce the polynomial coefficients for z sub j. We plug z sub j into that polynomial transformation, and the transformed non-normal variable that we get out of that, I'm calling j. So we get the j variable out. We do something comparable with z sub k. We get the k variable. It's non-normally distributed. So the question is these 2 standard normal random variables started with some correlation. And the question is that the same correlation that we end with once we've transformed those 2 variables using the polynomial transformation? What do you think? What's your instinct tell you? It's going to be the same correlation.
My instinct is no.
Yeah, mine too. So that correlation is not the same. It's going to be something different. Now the good news though is that the correlation is going to change in mathematically predictable ways. So since we can predict how that correlation is going to change based on the polynomial transformations that we performed, all we have to do is reverse engineer that process. And we can figure out what correlation we need to start with to get the correlation we want at the end. We have some terminology for this. The correlation that we start with the standard normal random variables, we call that the intermediate correlation. And then the correlation that we want the non-normal variables to have after the transformation is what we call a specified correlation. So again, the intermediate correlation is the correlation that we need to start with in order to end up with a specified correlation in the end. So we're going to return to conventional moments for a moment, just to look at how we address these intermediate correlations. So this is based on, again, another seminal psychometric article 5 years later, Vail and Morelli. They came up with this formula at the top of the slide here, and that shows how our specified correlation, rho sub jk, our specified correlation, rho sub jk, comes from, or arises from, our intermediate correlation, r sub jk, as well as those polynomial coefficients for the j variable and the k variable. So again, all we need to do here is plug in our value for the specified correlation, plug in our values for those polynomial coefficients that I already showed how we get those, and then we can solve for the intermediate correlation that we're going to need. Now, down below here in these two tables are values of the specified correlations and then values of the corresponding intermediate correlations. And if you kind of look across here, you'll see that the values of the intermediate correlations are just a little bit off. And so then after we perform the transformation, we should end up back at the specified correlation that we want. So now that was the conventional approach, applying this to the percentiles approach. Now we have the multivariate percentile power method transformation, and we're using the Spearman correlation for this. So C sub jk is our specified Spearman correlation, and you can see here that it arises from the sample size, n, so how big of a sample do we want to simulate, as well as the intermediate correlation, r sub jk. And again, we can go ahead and plug in our desired sample size, we can plug in our specified Spearman correlation, and we can go ahead and solve for the intermediate correlation that we need. Again, I provided an example here. You'll see that this is a little bit different. Here's, we've kept the same values. These are our specified Spearman correlations now. And you can see that when we solve this equation up here, we end up with values that are, again, a little bit off from the values that we want. So after performing the percentile power method transformation, we'll be back to the original Spearman correlations that we want. But these values are also a little bit different from the ones that were on the previous slide. They're a little different than the values that we get with the conventional approach. So putting it all together, this is what the process looks like. We're going to start off with our percentiles, and we're going to obtain our polynomial coefficients using that closed form solution that I showed you earlier. We will then specify our Spearman correlations for each pair of variables that's going to be subjected to our transformation. We will solve for intermediate correlations. The intermediate correlations are still going to be Pearson correlations. We will then simulate random normal variables with the intermediate correlations, and we'll actually use a Koleski factorization of that intermediate correlation matrix. And then finally, once we have those standard normal random variables simulated with the intermediate correlations, we'll then just apply that P of Z transformation where there will be several transformations, there's one for each variable. We'll apply the P of Z polynomial transformations using the coefficients that we had in our first step. So ideally, when we're finished with this process, what we should have is non-normally distributed variables with the exact non-normal distribution that we intended and the correlations that we intended, the intended Spearman correlations. So let's see how well that works. We did a little simulation study to see how well do we recover the parameters of the distribution and the correlations. So we used Fortran to generate 25,000 samples for each of these conditions. We chose sample sizes of either 25, a pretty small sample size, or 750, fairly large sample size. And we produced bootstrapped estimates of the median using 10,000 resamples. And we used 4 representative distributions. I'll go through those briefly here. So the first distribution was one that was symmetric, but extremely leptokurtic. And so it had a skew of 0, excess kurtosis of 25. And you can see down here, these are the coefficients for the conventional approach and the percentile approach for this particular distribution. Second distribution was positively skewed and still had extremely high kurtosis. So now we have a skew of 3, excess kurtosis of 21. Third distribution is positively skewed, so skew of 2, and moderately kurtotic, so kurtosis value, excess kurtosis value of 7. And then finally, for comparison purposes, because of course you can simulate a situation where you have a normally distributed variable correlated with a non-normally distributed variable. So for comparison purposes, our fourth distribution is just a standard normal distribution. All right, so let's look at the results that we have from this study, and I'm going to show you several slides. They're all laid out essentially the same way. So the upper half of the table is the conventional power method approach. The lower half of the table is the percentile power method approach. There's a lot of details in these tables. These are the tables from our paper. There's a lot of details in the table, but where I want you to focus your energy is right here on this last column. This is the relative bias column. And so what you can see is with the conventional approach, and this table includes the recovery of the measures of skew and kurtosis. For the conventional approach, we see double-digit percentage relative bias for the conventional power method transformation. We don't see any bias in places where we wouldn't expect to see it. So for example, distribution 1 is symmetric, so for skew we don't get any bias. Likewise with the normal distribution, the skew and the kurtosis, no bias there. But for all the other distributions, double-digit percentage relative bias. For the percentile power method approach, we do see some bias, but it's always on the magnitude of less than 3%. So a big difference between those two. And again, this is for sample size of 25, so this is our smaller sample size. All right, this is for the correlations in the correlation matrices that I showed you earlier. For the conventional approach, we get relative bias on the magnitude of about 3.5% to about 7.5%. Again, this is with the sample size of 25. For the percentile power method, it's better. It's running on the magnitude of about 1.75% to about 3.25%. Let's look at the larger sample size. Results are still pretty dramatic here. Again, for sample size of 750, this is for the skew and the kurtosis values. The recovery, we're still seeing double-digit percentage relative bias here. But for the percentile power method transformation, there were just a couple of instances here where the parameter value fell just outside of the confidence interval. So not really a notable level of bias for the percentile power method with a large sample size of 750.
In the bias, there is no digit means some.
I'm sorry?
The bias is 0%. You meant some dots, without numbers on the bias column. So on the very right side.
Right here,
Yeah,
the 5 dashes.
Yeah, that means 0 bias or.
I'm trying to remember. I think what happened. See, the double dashes mean the parameter was inside the confidence interval, so no relative bias really to speak of, so we didn't even bother to compute it. This one is different, and I'm trying to remember from the paper what happened. It seems to me that in this case, the estimate was so tiny that the calculation blew up, essentially. So we weren't, the 5 dashes here indicate we weren't able to get a value. Whereas here, we're saying the value is not statistically significant because the parameter is inside the confidence interval. Good question. All right, look at the results for the correlation. This is probably the best looking slide out of the 4. We still have some relative bias in recovering the correlations with the conventional method, but they're all in the magnitude of less than 1%. Down here, again, we kind of ended up with a situation where a couple of them were just outside of the confidence interval, and so we have relative bias on the magnitude of 0.02% or 0.05%. So the percentiles power method is working especially well even with the large sample size. It wasn't doing too bad with the small sample size, but it's doing really, really well with the large sample size. Now, earlier we talked about the multivariate percentile power method with the Spearman correlation. But we run into a little bit of an issue there with application that often we don't have the Spearman correlation. Often what we have is a Pearson correlation that's been provided to us. So it is possible to perform this transformation with a specified Pearson correlation. And this equation shows how to do it. It's a bit of an involved equation, so we broke it down into a few pieces here. But we can see that most of this is just a function of the coefficients. So again, we've already calculated those coefficients. We can go ahead and plug them in here. We know what our specified correlation value is, and so then we can just solve for the intermediate correlation that we would need to produce in order to achieve the specified correlation after the transformation. And you notice here we have to standardize it, so we're subtracting off the product of the means. It's the mean for the j variable and the mean for the k variable. Here's how we calculate the mean of the j variable. It arises as a function of the polynomial coefficients, which we already have. We have to do the same thing with the variances of the two variables. And so for the variable j, you can see how we computed that down here.
Jennifer, all coefficients or some powers or combination is just coming from some model, or how to get such numbers? Or
How to get these coefficients?
Yes, maybe 2, 6, 15 somewhere, is 3 or something.
Oh, where did these constants come from?
Well, how they are determined.
Trying to think how to simplify this. They're determined just based on basic algebra. So, in order to make sure we don't screw up the algebra, we end up plugging it into Mathematica. But these are straightforward coefficients that are coming out of just plugging in.
So you have some model, and then to make some mathematical equation, and then you can use the algebra, and then you make some this
Right.
kind of
So in order to get the equations, we're plugging in the percentiles of a standard normal distribution.
Okay.
We can plug that in and get the polynomial expression for the standard normal distribution, and then we can plug that into the formula for really any statistic we want. So I showed earlier how we did that for the 4 moment-like parameters, but you can plug that into any other formula as well, And so what happens is some things cancel out, some things get multiplied, and so then we end up with an expression that looks like this.
It's quite many variables actually.
It looks really complicated, doesn't it? But I mean, it's really just pretty straightforward algebra. I mean, other than having to reverse engineer this, you need a solver algorithm usually to come up with, well, I mean, we need the roots to come up with the coefficient.
What kind of
so-
solver do you use?
I'm sorry?
What kind of solver?
I'm trying to think of the name of it. Bisection method is what I used in the algorithm that I'm going to show you.
You're using MATLAB?
MATLAB, no. I was using Mathematica.
Mathematica.
Did I say MATLAB a few moments
I
ago?
just can't remember.
No, we use Mathematica, and then I just transferred the algorithm to SAS. So for people who don't use Mathematica, we had a journal editor who was like, "Our readership doesn't use Mathematica." So like, okay, fair enough. We'll come up with a way of doing this in some other software that the readership of that journal does use. All right, so for a moment here, I'll get to the SAS macro in just a moment here. But for a moment, let's talk application. So why would we use this technique? I'm coming from the College of Education and Human Services. Why are we interested in this type of technique? Well, the reason is because more and more these days we're seeing laws that restrict access to individually identifiable data. We're concerned about privacy, and so more and more these days we're passing privacy laws. And so this technique is useful for secondary data analysis of data that's collected in settings that restrict access to that data. So a great example in education is we have the law called the Family Educational Rights and Privacy Act, better known as FERPA. And then you might be even more familiar with in healthcare, part of HIPAA, the Health Insurance Portability and Accountability Act, has some provisions that restrict access to individually identifiable data. And so when we want to do some analysis, we might be restricted to descriptive statistics that are provided to us so that we're not seeing any individually identifiable records. And those descriptive statistics, the most common ones that we're going to see are going to be means, standard deviations, percentiles, and correlations. So that's what we have to work with in order, if we want to work around these laws. So we've created a user-friendly SAS macro. You can do this in Mathematica, of course, but we've created a user-friendly SAS macro, and it's available for download with our open access article that was published earlier this year in 2016. And this is the URL to access that macro, or the article and the macro download. You don't have to worry too much about writing down this URL. It's the same one that's at the end of the abstract for this talk. So I figured I'm going to make it very straightforward for you. The abstract was sent out to you in advance of this talk. You have the URL. If you go to this URL, you'll access our article, and then you can also download the SAS macro from there. And if you look in the references for the article, you'll also find our 2015 paper, which is the paper with the theory. How did we come up with all these equations? Where did they come from? And so forth. That's our 2015 paper, and it's cited in this one because this one is how do you implement this in a macro. So you can trace everything back from here. All right, so what's in the macro? Well, we have both univariate and multivariate options, and the multivariate option includes both the option for specified Spearman correlations and the specified Pearson correlations. Now, in order to use the macro, you don't have to have a lot of facility with SAS. Obviously, you have to have access to the software, but if you can copy, paste, and make some slight modifications, you can run this in SAS. So, first of all, you have to tell SAS where the macro file is, because I've done all the programming, and it's all in this sim.ppm.sas file that you can download. So you're going to include these two lines of code. Just copy and paste these two lines of code into SAS and submit them. The only thing you have to change is here you have to say where the directory, what the directory is that you put that file in. So if I put it in the SAS folder on my C drive, I'll put C:/SAS and then that's it. That's inside the quotation marks, and everything else here stays the same because the file name is already here. Everything stays the same here, and so you just submit these 2 lines. Now SAS knows where that macro is, and so when you want to call that macro, when you want to invoke that macro, it knows where to go to find the code. All right, now, if we're going to go ahead and invoke this macro, call this macro, we're going to need 7 things. So for starters, we're going to need to tell it how many variables we want it to produce. Second, we're going to have an external file with the percentiles in it, so we just need to tell it where that file is and what the name of that file is. Same thing with the specified correlations. Those are going to be in an external file, and we'll have to tell it where that file is and what it's called. We'll have to give an indication of whether the specified correlations are Spearman or Pearson. So I set it up so 1 is Pearson, 2 is Spearman. By the way, 3 and 4 here, the correlation file and whether the specified correlations are Pearson or Spearman, that's for the multivariate approach only. So obviously if you say we're only simulating 1 variable, that information is irrelevant. We also need to tell it our desired sample size. Do we want a sample size of 25? Do we want a sample size of 750? We have to tell it exactly what we want. We also need to give it a random number seed. That's optional. If you don't provide the random number seed, this will still work. The problem is that you will not be able to exactly replicate what you just did. I'll show you that in a moment here. And then finally, we want it to simulate this non-normal data, so we have to tell it where and the name of the file in which to put that data. All right, so we're going to walk through a couple of examples here. The first example is an education example with the Idaho State Achievement Test. And we want to produce mathematics scale scores for 25 third graders. And we were able to do this because they had their percentile rank conversion tables publicly available. So we used the 2011 scale score to percentile rank conversion tables to obtain the percentiles to use this approach. Here, this line right here is the call to the sim-ppm macro. So the 1 indicates that we're just simulating 1 variable. We just want the math scale scores. Then we have a comma. This next item is the percentiles file. It's the location of the percentiles file. So I have a file, it's a text file, that I called ex1, example1, percentiles.txt, and I saved it in the C drive in the SAS folder. So SAS folder on the C drive, and so I go ahead and put the full file path and